This video is about component tolerances. It corresponds to section 11.9 of Applied Analog Electronics. Okay, when we do a design, we generally say we want a particular resistance value. Like we might say, okay, I've got a resistor 10k ohms. But when we actually put a resistor in the circuit, it's not going to be exactly 10k ohms because they vary a little bit from instance to instance because of fluctuations in the manufacturing. They also vary a bit because of temperature. Now, resistors nowadays can be obtained with different tolerances. You'll often find tolerances of about plus or minus 1%. Okay, and what that would mean is that the 10k ohms there isn't necessarily 10k ohms. All they're guaranteeing is that it's in the range 9.9k ohms to 10.1 k ohms. And that guarantee actually, when they give that, that's at 25 degrees C. You can also pretty easily nowadays get 0.1% tolerance, and there it's 9.99 k ohms to 10.01 k ohms, so a much more precise value. And again, it's at 25 degrees C. And you might wonder, well, why doesn't everybody just use the more precise ones? Well, there's a good reason. They're more expensive. So the 1% ones are very cheap. And those are what sort of is the default value to use if you're just saying, hey, I need a resistor here. I'm not that fussy about the value. The 1% resistors are pretty much the cheapest ones on the market. There are some older ones around, which are plus or minus 5%. And those are done in a different way. Those are not metal film the way the 1% and 0.1% are. Those are carbon resistors. And this is an older technology. Back when I was a kid, they were almost all carbon resistors because that was what was the cheap technology then. They're hard to make precise, and they're not used much anymore because these plus or minus 5% resistors aren't really any cheaper, or very, very, very tiny bit cheaper than the plus or minus 1% ones. So they're kind of gone, but you'll still see them in some old designs. You take apart some hardware from the 60s or something, you'll see carbon resistors in there instead of metal film resistors. Actually, there are three types of resistors commonly available. The ones I've been talking about that we use in class are the metal film ones. And they basically consist of some sort of ceramic substrate or other substrate with a thin layer of metal on it, the metal film. And that metal film then is patterned usually by some sort of lithography process or something to get the resistance that you want. The carbon one is more of a sort of block of a material. There's another type called wire wound, and this is probably an older technology than either the carbon or the metal film one. You just take a length of a fairly resistive metal and you wind up a big length of it in order to get the resistance you need. Wire wound resistors are still found when you need high power. Okay, the carbon resistors can't take all that much power. You get 1 or 2 watts usually out of that at the most. Quarter watt is standard. The metal film ones, because they're a very thin layer of metal, generally can't dissipate much heat without evaporating the metal. And so those are generally like quarter watt, sometimes 1/8 watt, generally fairly small power. If you want to dissipate a lot of power in your resistor, then you use the wire wound ones, and you can get those 100 watt easily. They often have cooling fins and other things on them to dissipate the heat. All the metal ones have a positive temperature coefficient, positive thermal coefficient. And depending exactly what metal they use, the coefficient can be different, but typically it might be something like 50 parts per million per Kelvin. Sometimes written as per degree C, because 1 Kelvin is a step of 1 degree in Celsius also. All right, so if you've got a 50 parts per million in Kelvin 50 parts per million per Kelvin, and you can take the thing up to 125 or maybe 150 degrees C, so that's plus 125 Kelvin. 50 parts per million times 125 Kelvin, that's going to be about 0.625%. Okay, so that 1% precision we had there, that's at 25 degrees C. You've got another 0.6% possible increase in its value as a result of getting it hot. Or if you get it really cold, then it drops in value. So this 1% is not across the entire temperature range, that's just at 25 degrees C. You have another 0.5%. So that's another reason why people don't use the 0.1% much, because they usually have a thermal coefficient that's not that much smaller than this. And so you have to, if you really need the precision, you have to be careful about getting it at the right temperature, as well as or compensating for the temperature changes. They're not perfectly 0.1% across the entire temperature range. Okay, that's probably all we need to say about resistors. Oh, one more thing about that. The carbon resistors do sometimes get used because they have a negative thermal coefficient. And so sometimes you'll see, particularly in some older circuits, where they're getting used to do some thermal compensation so that the circuit behaves the same way across a wider temperature range. And then if you replace them with the metal film resistors, which have a different thermal coefficient, their behavior across a temperature range may be different. So some of the very early electronic synthesizers, the stuff from the early 60s and stuff, was designed around carbon resistors, and if you replace them, take exactly the same circuit and replace the carbon resistors with metal film resistors, you may find it doesn't work exactly the same way, and that as temperature changes, it may go out of tuning and stuff because they went to a lot of work to make the thermal coefficients of the resistors and stuff compensate for changes, and now it's not compensating in the same way. Okay. Let's look at capacitors. Capacitors, again, we may be specifying something like, we want 100 nanofarads. What sort of range do we actually get? And there it depends a lot on what sort of capacitor we're putting in. You can get film capacitors. And these are generally something like a plastic like mylar with a layer of metal plated onto it or coated onto it somehow. You can get ceramic capacitors, particularly, and there's several different types of ones. So there's C0G or NP0. Those are the good ceramic capacitors. And then we have the cheap ones. You can get ones that have dielectrics like X7R or Y5V. And you can look up in, I think, the capacitor chapter, I talked a little bit about what these codes mean. They're referring to the different dielectrics that can be used in the ceramics. Now the C0G and the NP0 is not a very high dielectric constant, so you don't get really big capacitors with those, but they're like plus or minus 5% on the tolerances, and that's across the whole temperature range. So unlike the resistors, there's not usually a big thermal coefficient on the capacitors. There may be some, and the better manufacturers may tell you a little bit about it. The film capacitors, they also are using a fairly low dielectric constant. They're usually using some sort of plastic or something, so the dielectric constant is only around 2 or so. And so again, you can't get very big values unless you get really large, physically large capacitors. The high dielectric ones, the X7R, the Y5V, those you can get moderately big capacitors. I mean, you can get up into the tens of microfarads. And here the X7R is going to be something like plus or minus 10%. So not quite as good as the C0G. but still quite reasonable. Um, and then the Y5V, those are something like, I think that's plus 80% or minus 20%. Not even a symmetric range. Um, and those are still useful because you can get fairly large capacitors here. You can use those things for things like bypass capacitors, where if it's bigger, it's actually better. You don't really care if it's too big a capacitor. What you mainly care about is that not get too much smaller. And so it's not a precise value you need. You just need, hey, I need a big capacitor here to, you know, let the high frequencies through and charge up, store charge. So I need a pretty big capacitor in order to store enough charge. Um, and so the Y5V capacitors can be useful there. They're very cheap. Um, they're also fairly small. There's one other type here, electrolytic. And there you really have to look up the specs for the individual ones because they vary quite a bit in their tolerances. But quite often they have tolerances kind of like the Y5V of very wide ranges. And again, the electrolytic capacitors are mainly used when you need to store a lot of charge, and it's the charge storage you care about. It's not so much the precise value of the capacitor. Um, and, well, there's one other thing you have to worry about with these high dielectric capacitor, ceramic capacitors, and that is those values are small signal values. That is to say, those values are for tiny voltages. So when you haven't got any charge stored in the capacitor, if it's just got a 0 volt bias across it, then your capacitances are about what you expect, plus or minus 10% for the X7R and stuff. But what happens with the high dielectric ones, so the ones that have these codes or codes like those, is that when you put a DC bias across the capacitor, the dipoles that are inside the dielectric that give it its capacitance, give it its high dielectric constant, those dipoles get aligned to the field and no longer flip back and forth, and as a result, the effective capacitance drops considerably. And so you generally use sort of rule of thumb, use no more than like 20% of rated voltage for the high dielectric constant ceramics. What that means is that if you're running and that 20% is a very rough rule of thumb. If you're running a 3.3 volt system, well, then you want to use about 16 volt capacitors. And now that's only if you care that the capacitance doesn't drop. If you want the capacitance to be close to the rated capacitance, then you don't put a large DC bias on it. If you've got something where you don't care, you say, hey, I just need a big capacitor here. I need about 1 microfarad, but I'll put in a 5 microfarad capacitor and I don't care if it drops to 1. Then you don't have to do this no more than 20% because if the capacitance drops somewhat, it's not a big deal. And it's only if you're trying to use this thing for something like a filter, something like that. Then you care about, all right, I want this thing not to change its value with the voltage. The film capacitors and the COG-NP0 capacitors, those don't have the same sort of problem. You can use them pretty much up to the rated voltage without problems. I mean, the film capacitors particularly, the rated voltage there is just at what point you start damaging the plastic. And it's not going to change its characteristics as a result of the DC field on it. Okay, so capacitors, a little bit different situation than for resistors. Again, the cheapest ones here may not be that precise. And the ones that we have in class, I don't have any idea what dielectric they use. They're not labeled, and they're probably the cheapest, which is usually the Wi-Fi V or something like that. And so they may be quite a ways off from the ideal capacitance. So if you're trying to do something which is a carefully tuned filter, you probably don't want to use those really cheap capacitors we had in class. But if you just need something approximately right, I mean, where you don't mind being 20 or 30% off, then they're fine. If you do care, slightly more expensive C0G and P0 capacitors are probably the main choice that people make these days. If you need huge capacitance, so if you're looking for something more than about 10 microfarads, then you end up using the electrolytics. And for the electrolytics, you can get quite large capacitors. Fairly routine to get something that's 1,000 microfarads, so a millifarad. And if you need to, you can even get what are called supercapacitors, which are basically electrolytic capacitors that you can get in the farads. So we're talking about millions of times bigger than these little ceramic ones, and you can store quite a bit of charge on them. They don't go to very high voltage. The supercapacitors usually have a very low voltage limit because they're very, very thin films of the insulator. And so put too much voltage across it and you break down the dielectric. So those tend to be something like 1.8 volts, but a farad or more. Special case of electrolytics. I've not had much use for the supercapacitors because I don't usually need very large capacitances at low voltages, but they exist.